This is a production of Cornell University.
Another good example, and this has nothing to do with urban, this has to do with climate. Okay? What we look at here is this line right here represents amplitude. Okay? And this is the time of year. Okay? So the time of year, amplitude. Okay? And what you're looking at here, these dotted lines right here are rainfall. Okay? So a eutic moisture regime, pretty consistent rainfall. Yeah, there's going to be some stratification in there. You have big storm events and small storm events, but pretty much you have rainfall all through the entire year. Okay? In this system, we're looking at a eustic system where we have sort of a monsoonal type of event. In this case, it's a bimodal monsoon. Okay? We have a distinct dry period and we have distinct wet periods. Make sense? Okay. Now, what we look at, this dashed line is nitrate N, excuse me, that is in the cropped soil. The solid line is the nitrate N that is in the bare soil. No crops. Okay? So let's take the top example. It's raining all the time. This is basically the growing season right here. We put our plants in. What happens to the nitrates that are in a cropped soil versus in an uncropped soil? The nitrate numbers. Well, in the crop soil, what happens to my nitrate numbers? They drop. Why? The plants are growing. They're sucking that nitrogen up, right? Does that make sense? Okay. But notice what happens in the bare soil. What happens to the nitrate N in the bare soil? Goes up. Why? There's nothing being removed from the system, but if there's nothing being removed, you probably should have a nice flat line. But we're seeing an increase in nitrate. What's happening? What's happening is nitrification. This might be the growing season for crops, but if I have a warmer temperature, I'm going to have more biological activity, which means I'm going to have more nitrification. Does that make sense? When we're talking about climate, what's this? Wintertime, summertime. Wintertime, summertime, right? And if microbial populations are driving this cycle, if the microbes are driving this cycle, it means this part of the cycle, when the temperature increases, that means that this cycle is going to increase, which means I'm going to have more of this. Does that make sense? Go.
Would it also just be because of greater nitrogen fixation too in those systems?
Well, if I got N fixation,
Then you have greater.
one would assume at this time of the year, nitrogen fixation, if this line represented biomass, I'd say yeah. But this line represents nitrate. And that's what we're seeing. Do the same thing for here. It's basically, in this case, we have an increase of rainfall. We have an increase in the cropped land as well as an increase in the uncropped. What's going on there? Okay, in this case, this is going down. Okay, so we can make the explanation. Okay, we can understand the bare soil. Okay, I got more moisture. This is pretty much a uniform temperature area. Okay, but I have more moisture, so I'm having an increase in biological activity. Why am I also getting an increase in the crop soil? I mean, you would think, well, increased crop soil, I'd have increased nitrate removal, right? Well, the plants, I mean, it's a uniform temperature. You would think that these are both, the growing season has nothing to do with temperature. The growing season actually has more to do with water. So you'd almost have two growing seasons here.
Is it a little bit delayed after things start to dry? Like, does it not start until after?
Well, that could be. So you're really thinking most of the production is here. Most of the production is here. It's not actually at this peak. Because this is where you're getting germination. And actually that is, in fact, part of it. We're looking at a combination of wet soils. I mean, the soils are getting wet, and And we're seeing a delayed growing season, which then drops this down. And you'll note that, look, this drop right here, see how the bare soil versus the drop that's in the crop soil. This is where you're seeing the crop response, taking that nitrate up. But I still have this point right here. The answer is right. What's going on, though? What's going on at this end versus this end? So this part of the curve versus this part of the curve. This part of the curve, these two lines are basically together. This part of the curve, these two lines are separated. And the answer there is the crops. What's going on here?
So you said that in anaerobic zones that
Denitrification.
denitrification is taking place.
Right.
So how could it possibly be that it goes up when
Well, these systems are not necessarily saturated. I mean, we could use this curve, and I could change this to water. There has to be a certain amount of water to have biological activity. When it starts going down, we're starting to see anaerobic conditions. But here, it's not anaerobic. It just has a lot of water, but it's not so much that it's anaerobic. So there's another hand raised over there. And actually, this is the answer. But the question is, what type of biological activity? This is plants starting to suck those nitrates up. But who's producing those nitrates? Andrew, is that what you're going to say?
Well, yeah.
The microbial population responds like that. So it doesn't matter if I'm in the bare soil or in crop soil. The plants, on the other hand, are not necessarily responding yet. Okay, so I have this nice little peak, and then we see the drop. Does that make sense? You need to have the nitrate made. Something has to make it. Okay, and then it gets sucked up by the plants. And this is the microbial population that's making it. Go.
So is the peak, like that peak is caused by generally just the plants begin to produce at that point, or they begin to?
This is when the plants start taking it away. Okay, all you're seeing here is the plants aren't active enough to take all the nitrate away. Go.
would forested or grassland systems that aren't cultivated crops behave like the crop system?
Grass systems probably would. Forested systems, I'm not so sure, because even in cold times, forested systems are actually taking up some nutrients. But I suspect you would still see this type of. The microbial population is going to respond a lot faster than the plants, and then when the plants start sucking it up, that's when you're going to start seeing it. Okay, cool beans. Questions? All right, let's stay on controls. You've seen this slide before. What controls these fluxes? Well, the nitrogen controls. The nutrient itself controls the fluxes. And you've seen this one. This is ammonification, very much paired with nitrification. I can't have nitrification without the ammonium. All right? And then I start seeing denitrification because I can only get denitrification when I have that nitrate. Okay? Now, we're also looking at the pore volume issue here, but we're basically seeing a sequence of processes. Make sense? How about we take a look at denitrification? Okay, so we start with nitrate and we end with N2 gas. Okay, basically what you're looking at is a time scale here, a period of time, and a concentration. The higher it up it is, the higher the concentration. Okay, so we start this system at the end of nitrification, where I have lots of nitrate. Okay, the system goes anaerobic. What happens? Well, we start seeing the creation of N2O gas. Okay, and with the creation of N2O gas, the next sequence, the next step in this denitrification is N2 gas formation. And as we see this go down, we see the N2O gas start increasing, and then this is then converted into N2 gas, and we start seeing that increase. And the NO3 crashes. Sequence of events. It's the form of that nitrogen that controls the reaction. If I did not have this, I would not get this or this. If I didn't have this, I would not be getting that. Does that make sense to everybody? Go, Andrew.
So all that's anaerobic?
This is all anaerobic.
What basically controls whether N2, like nitrous oxide is produced or N2 gas is produced?
What controls whether this is produced or this is produced? Well, this controls this. Oh, it's a microbial population. It's a microbial mediated reaction. Okay? The microbial organisms are taking that and converting it into that. And then another group of microbes that are living in the same environment are taking this and converting it to that. And so this controls this controls that. Ultimately, this controls that. You have to have the nitrate to get the denitrification. Does that make sense to everybody? Questions? We cool? Good deal. All right, so those are the controls. What, in fact, are the consequences? And you're going to see this same thing again and again and again, depending upon what nutrient. We're going to be looking at plant growth. We're going to be looking at leaching and eutrophication. We're going to be looking at acidification and toxicity. This graph could be any nutrient, with a couple exceptions, potassium being one of them. Okay? We have a certain range of that nutrient, of its availability. So this is the plant response, okay, and this is the amount of nutrient. Okay, as I'm going that way, I'm looking at an increased amount of a nutrient. There's certainly a phase where the plants, they're deficit in that nutrient. And if they're deficit in that nutrient, they're not going to have optimum performance. Somewhere down the line, they're going to get the amount of nutrient they need to perform, and we're going to start seeing a sufficiency range or their optimum performance. Now, depending upon the type of nutrient, in some cases you'll reach a toxicity zone, and in some cases you'll get a range that we call the luxuriant range. Okay? In some cases that nutrient becomes a toxic element or a toxic factor in the soil, and in some cases it doesn't do anything. Okay? And it just sort of sits here and the plant doesn't perform any better than it did at this level. Okay? Potassium is a really good example of that. Okay? Nitrate, you get high levels of nitrate, high levels of ammonium, and you see this type of response. Okay? Now, another effect with nitrate and nitrogen in general is pH. If I start forcing my nitrates this way, lots of nitrates, what I'm going to see is I'm actually going to see a drop in pH. Okay? What you're looking at here is nitrogen fertilization application rates, and this is pH, 7, 6, 5, 4. As my nitrogen, I start applying my nitrogen more and more and more and more, I'm going to see a drop in my pH. Part of the consequence. Toxicity. This is a concentration. This is actually ammonium that's in water. Okay, and this is a fish toxicity response. Okay, what we're looking at here is pH, and we're looking at temperatures. These numbers basically represent the concentration at which the water becomes toxic to the fish. Okay, so the lower the concentration, the more, I should say, the whatever this number is, depending upon whatever its condition is in temperature and pH wise, that number at and below, or that number and above, is toxic to the fish. Okay, so if this is my ppm at pH of 7, this is parts per million ammonium, at 15 degrees Celsius and 7, if I have a ppm of 7.4 or greater, I'm going to have a toxic response in my fish. Does that make sense? You'll note that as the pH rises and as the temperature rises, that concentration number gets lower and lower and lower. When I start getting to the pH ranges of 8.4 and at a 25 degrees Celsius temperature, that's pretty warm, my toxicity of parts per million is 0.1. Now, this would be really low from a nutrient sense point for the plants if it was in a soil, but this is really high for the toxicity of plants, for the toxicity of fish. Now, compared to this, yes, this is a lower number than that, but that's a high toxicity at a very low number. Does that make sense? The consequence of that nutrient cycle.
Wait, so are you saying that a lower concentration is more toxic to the fish?
At at higher temperatures and higher pHs, a lower parts per million in the water is just as toxic to fish as a higher concentration at a lower temperature and a lower pH.
Kind of one's like 19 degrees and 7.6 pH with...
If it's 19 degrees and 7.6, if the concentration is less than 1.5, they're fine.
Okay.
If it's greater than 1.5, they're dying. Does that make sense? Big sigh. Questions? We feel comfortable with the nitrogen cycle. We feel comfortable with the pools and the fluxes and the controls. Okay? Because as a farmer or as a waste manager or as a homeowner, these are the types of things that you should be thinking about when you're applying fertilizer or you're managing your waste. Okay?
This has been a production of Cornell University, on the web at cornell.edu.